Okay, let's continue. For the plate bending element, and especially for the Hermite plate element, we have three displacement functions we need to define if we like to describe the displacement functions for this element. First, we have the xy plane. And we need to have the cosine eta plane. Okay. Let's assume the plane include for the thin plate, it is the x and y plane. So first we will send the xi, yi. Okay, first we will send the nodal coordinates of the real element to the masked element, and the number of the nodes could be changed from the 4-node element, 9-node element, or 16-node element. It is assumed that we use the Lagrange shape functions. Also, you can choose the serendipity shape functions. Then we have another set of the number of the nodes. After we send the nodal coordinates to the masked element, then we can establish two continuous x and y functions in the masked element. And also we need to assume the nodal displacements and then send them to the masked element to establish the continuous functions. The three displacement degrees of freedom. Okay. For each nodal point, we need to assume three displacements. First, the Wi, which is the vertical displacement along the z directions. Okay. So remember the plate bending element, we consider only the vertical loadings. The vertical loadings means which is normal to the plane. So it is the z direction. All the applied loading must be along the z directions, and so the vertical displacement along the z direction, which is the w displacement, which is a very important displacement we need to consider. Also, we have two rotations. The rotations about the x-axis, the theta y rotations about the y-axis, and also we need to assume these two rotations for each nodal point. And also we will send the three nodal displacements to the masked elements. Then we can establish they should be the cosine eta. So after we send the nodal displacement to the masked element, then we can use the shape functions to establish three continuous functions, w, theta x, and the theta y in the masked element. Okay, print the screen, then I will continue. Okay, first, the displacement the displacement functions for the neutral plane. The neutral plane is usually located at the middle of the plate. So the most of the time they are at the middle layer of the plate. Okay, so the displacement functions for this element, u of Cassier eta, equal to 0, and first, for the neutral plane, the horizontal displacements on the same plane, u and the v functions, they should be equal to zeros. Remember, we assume for the plate bending elements, all the applied loadings will be perpendicular to the plane. So the horizontal displacements along the same plane, the u and the v displacements, they should be equal to zeros. Okay. Also, we have the displacement the z equal to 0 represents the points on the neutral plane. But for the points which is the z not equal to 0, it means they are the points considered for different layers other than the neutral plane. Okay, for the displacements for z not equal to 0, and it means for the w displacements will be same as the point there, and also the u displacements will be the theta y times phi represents the theta y for the considered point. The considered point could be other than the Cassier and eta only for the nodal points. Originally, we just assumed the theta yi for those nodal points, but after we use the shape functions, then we can get continuous functions throughout the masked element. So in this case, for any Cassier and eta, for any point in the masked element, we can use the assume the theta yi and the shape functions to get the theta y for the considered point. Then we need to multiply the theta y by the z values. Okay, then you need to image, there is an axis, and the axis rotates about the y-axis by the angle theta y, and for these rotations of the axis will create the displacement. It will create the displacement along the x directions. So we need to multiply the z to the rotations to the rotation angle theta y, then we can get the corresponding displacements along the x directions. Okay, the same situations can be used to consider the displacement along the y directions. So they will be the v. Okay, so also we can use since the theta xi, they are the assumed nodal displacements. Theta xi times phi will be the theta x for the considered point, and then we can multiply the theta xi by the z values. But you should follow the right hand rules. The positive theta x will be the rotations in these directions. But for positive also, if we combine the positive theta x and the positive z values, it will create the displacement to the negative y direction. So you need to add a negative sign. You need to add an active sign, negative sign to correct the displacements. Okay, so here is a negative sign. Okay, just print the screen, then I will continue. Okay, then the next step, how do we calculate the strength inside the element? Okay, and there are 5 strengths we need to consider. The only missing will be the epsilon z. Since the plate bending element, the geometry character for the plate bending element, it is still a thin plate. So the thickness of the plate, which is a relatively small dimension. So the normal strain along these small dimensions, it can be neglected. So that's why when we describe the displacement functions, all the w for different z value, if the x and y they are same, or you can say the c and the eta they are same. If the c and the eta they are same, for all the points along this axis, the w values they are all same. So in this case, it means we neglect the normal strain epsilon z. Okay, so for the plate bending element, there are 5 strains we need to consider. Ehrmacht's plate element, it is a thick plate element. It is based on the thick plate theory. Okay, if we use the thin plate theory, then the gamma yz and the gamma zx, the shear strain, which has along the z direction, there are 2 shear strain, theta yz and theta zx. for the thin plate element, these two also can be neglected. But for the thick plate elements, we will consider the shear strength inside the element. And also, we can still use the okay, so that's the you can say they are the old frame. We can, if we know the displacement functions, then we can calculate the partial derivatives to calculate the normal strength. Okay, the elongations for the unit length. Okay, and also we can use the partial derivatives to calculate the shear strength, the change of the angle. Okay, either from the horizontal axis or it is come from the vertical axis. Okay, so that's the basic formulas where we can use this formula to calculate the strength. However, for the plate bending element, there are two elements we can change it by the basic things. Okay, so they are the this term which is the negative theta x, the rotation about the vertical axis. For any point, the rotation, the partial v divided by partial z, which is the rotation about this one, and these rotations can be replaced by the negative theta x. And also for this one, partial u to partial z, which is the theta y, which is the theta y. Okay, and we need to use the assumed displacement functions to calculate the other terms. Let's take an example. How can we calculate the partial u to partial x? Okay. Remember, we assume the displacement functions first on the masked element. So we have the clear formula which can tell us how can we get the u of cosine eta and the v of cosine eta. Since these two functions, they are established on the masked element. So we know the u of cosine eta and the v of cosine eta. And the two parameters will be the cosine and the eta. So we will not directly to calculate this term. First, we will use the chain rule. You take partial derivatives to the cosine and eta, multiply by the partial cosine to partial x and the partial eta to partial x. Okay. And you should know how do we get these two terms. we need to calculate the Jacobi matrix first, and then we need to calculate the inverse matrix of the Jacobi matrix. So these two terms, they will come from the J inverse. Okay, so these two terms, they will come from the J inverse matrix. And I will not repeat how do we calculate the elements in the Jacobi matrix, since for the plane bending element, the description of the geometry, which is similar to the plane stress elements, we need to send the input nodal coordinates xi and yi to the mass element. After the mass element get the nodal coordinates xi and yi, then we can calculate the elements in the Jacobi matrix, and they are all in real numbers. So we can calculate the J inverse, the elements in the inverse of the Jacobi matrix, also in real numbers. So these two elements, we know their values as long as the Xi and the eta, they are given. Okay, so it means for any point inside the element, we can calculate the elements for the Jacobi matrix. Also, we can calculate the elements for the inverse Jacobi matrix. Okay, so these two elements, we know their values as long as the Xi and the eta, they are known. Okay, and how do we calculate these two? Remember, the U is equal to the Okay, since we know all the shape functions, no matter the number of the nodes for this element, we know all the phi functions, and for those known functions, we can calculate their derivatives about the Xi and their derivatives about the eta. So we can calculate the partial phi to partial Xi. Okay. But remember the z values, they are the z values related to the points you need to consider for this element. Under the theta yi, they are the assumed nodal displacements. For these two, they are not a function of the Xi. So we don't need to consider these two terms. Take the partial derivatives. According to the chain rules, we can multiply these two unchanged to the third term, take the partial derivatives. Okay, so in this way, we can calculate partial u to partial Xi. But right now, the theta yi, it is still unknown. So we will express this term by a row matrix multiplied by the column vector. The column vector includes the nodal displacements wi, theta xi, and the theta yi. And the row matrix, which is also one row for the B matrix. And you need to know how can we calculate the elements for the B matrix, and to derive how do we calculate the elements in the B matrix, it is an important step when you solve the problems by the finite element method, you need to know how can we calculate the strength inside the element. It is always an important step. Okay, so we can calculate these terms, also this term, and then we can express the okay, we can derive, if we put all the nodal displacements in the U vector, what elements it need to be multiplied to give you the epsilon x, to give you the epsilon x. Okay. Okay. I hope you can derive it then by yourself, since if you know the displacement functions, then how do we calculate the partial derivatives? Okay, and let's check how do we calculate this term, partial w to partial y. Okay, so that's the partial y to partial w. Okay. Okay. Print the screen. Okay, the next step, if you know how can we derive the elements for the B matrix, then the next step will be we will try to calculate the strain energy for this element. Okay. We will not calculate the strain energy for the entire structures. Usually we will derive how can we calculate the strain energy for one element, for a single element. And remember, the union of all the elements will always be the entire structures. So all the structures you would like to consider for your structure analysis problems, they must be covered by the defined elements. So you need to define the elements for all the structures. You cannot leave any part of the structure they are not covered. Okay, so you can add a subscript. the strain energy for a single element. Okay, how can we calculate the strain energy for a single element? And the strain energy for the entire structures will be the summations of the strain energy for all the elements Okay. Okay, and remember we can use the B matrix multiplied by the U displacements to calculate the strains considered inside the element. Okay, but there are several things you need to pay your attention. First, for the mapped and the inverse mapped elements, we do not describe the displacement functions directly on the xy plane. We will define the displacement functions for the mass element, then send the establish the displacement functions back to the real element. Okay, so we will not consider the change of the x and y directly. We will consider the change of the coordinates in the mass element. So they are the Cauchy and eta values. Okay, I think I will take a break here, and I will try to finish the description for the plate bending element in the next hour. So it could be the last part of this semester.